Good morning, everyone. I hope you enjoyed the opening keynote as much as I did. We're going to turn to something equally serious, but in a different way, and that's really the rising carbon footprint of HPC. And I use that in an expansive sense to talk not just about technical computing, but the energy footprint of hyperscalers and the rise of AI and the implications of that writ large. And so how we think about addressing that demand, not only for energy and the carbon effects, but also how we think about the demands on another limited resource that we often don't talk nearly enough about, and that's water. We have a panel of experts from a variety of different perspectives. I'm Dan Reed from the University of Utah. And we've got folks from Schneider Electric, from the University of Chicago, from HPE, and from the Finnish IT Center for Science, and from Los Alamos. So I thought I would start by framing the discussion. And here's the format. Each of the panelists is going to make an opening statement, and then we'll take questions from you and from those that are online. So I'm going to seed a few thoughts I want you to think about, but we really want this to be a lively back and forth. So it's not just a whole series of lectures, but a conversation between the panel and you about the future. So how did we get here? We know that HPC systems continue to grow, to deliver performance, and any of you who attended the top 500 list reveal yesterday know that our systems keep getting bigger, and largely that's because the free lunch of Moore's Law has slowed down. If you want more performance, you need to buy more hardware, and that means a bigger system, that means more energy dissipation, and more cooling demand. The thermal dissipation of individual packages keeps rising. And if you told me a few years ago that we'd be talking about TDP of a kilowatt or more per package, I would have probably laughed at you, but you could see that happening. And the other thing, of course, is we want dense packaging because, you know, if some of us have been consulted, we would have recommended a larger value for the speed of light. It's not nearly as fast as we might like in these circumstances, and so density is a way of reducing signal delays. 15 years ago, we really started to work on PUE, and traditional data centers and research drove PUE down pretty much as close to 1 as we can get it these days. And so the question is, where is the other set of opportunities to address energy efficiency and environmental efficiency writ large? And as I said, as we've moved through airside economization to water, water is a precious resource, certainly potable water, and it's increasingly limited, giving the large volume of water that's evaporative for evaporative cooling in larger systems. And that's increasingly constraining where some systems can geographically be placed. So put all that together, total energy and cooling costs keep rising. Energy is now a substantial fraction of OpEx, and the total energy costs over the lifetime of a machine is a substantial fraction of the CapEx. And the AI boom is driving that energy consumption even higher. If you look at the cost of an AI query compared to a traditional search, the per query energy cost is substantially higher. And these environmental issues are very real. So some of the things I want you to think about is, what do we do about this issue? How do we become part of the solution and not just part of the problem? So here's some questions that I suspect the panel will in different ways address, but they're seed and framing questions really for you to think about, questions you want to ask our panelists. What R&D do we need to shift the dynamics around computing sustainability? What are our biggest constraints? Are they economics? Are they policy? Or are they technology? And the answer is probably all of the above. How do we measure sustainability? And by analogy, if you think about total cost of ownership for a system, where do you draw the bounding box to charge for the energy and environmental costs? How do we reconcile our desire for ever increasing performance with sustainability? And how do we balance, as I said, CapEx and OpEx and timescales? And then how do we quantify, or what are the metrics, and how do we manage that carbon footprint? You know, the water issues, the greenhouse gases, the energy, and the waste issues. Those are all kind of framing thoughts to think about as we begin the discussion. And so with that, I will turn it over to our panelists to begin, and we will start with Rob. Do you want me to drive the slides up here, or do you want to come up?
Oh, yeah. Good. Yeah, I'll stand up. That's good. All right, good morning, everybody. I'm Rob Bunger from Schneider Electric. It is great to see this number of people interested in sustainability, so very encouraging. We've done a lot of thinking about what is environmental sustainability for data centers in general, and what would you even measure. And so this is a year and a half ago, and actually recently revised. We put out a proposal for a number of metrics that we think should be measured in order to capture the environmental sustainability of a data center. And it's in 5 categories, and this is not new to most everybody, but this is probably what you do. So, you know, how much energy you're using, what are the greenhouse gas emissions from the data center, water use, how much waste is generated, and the impact on the local ecosystem. And there's various metrics that I'll quickly go through underneath this. All data center operators are in a different spot with regards to measuring sustainability, and so we've broken it out into kind of 3 categories depending on where you're starting. From the beginning, where you'd maybe take a look at 6 out of the 28 metrics that we think would be great to measure, advanced 18, and leading would be 28. And my proposition is that the HPC community should be striving to be leading. They lead in all the other aspects of performance, and I think sustainability reporting and measuring should be one of them. So what are we talking about with regards to these metrics? This is what we recommend. So total energy consumption, straightforward. Power usage effectiveness, I guess the grandfather of data center metrics. Total renewable energy consumption, and that's an input into some other ISO standards like renewable energy factor, REF, energy reuse factor, which is gaining a lot of interest, especially over in Europe. And then this is something we added more recently, is just server utilization. And that might be an interesting one for HPC, depending on how, obviously, the workloads are being done. But for some other data centers, not so much. It should be tracked. So that's on the energy side. So how much energy are you consuming, and where is it coming from? In the greenhouse gas category, this is the largest list we have. So, you know, I apologize for the eye chart here. And so hopefully everybody has heard of or has a reasonable understanding of the scopes of Scope 1, Scope 2, Scope 3. The GHG protocol does a great job of explaining that. Scope 1 is stuff that you emit on site. Typically, we think of a traditional data center like the backup diesel generator would be in emissions on site. It could be driving around trucks. It could be leakage from medium voltage switchgear that has that SF6 gas, or it could be leakage from a refrigeration system that you have. Scope 2 is the stuff that comes from the purchase of electricity, and you want to break it out 2 ways. One, what is your local grid? You know, you're connected to a local grid. What is the mix there on the local grid for emissions? And then a lot of folks have power purchase agreements, or we'll call it market-based. So you might net yourself out to have 0 Scope 2, but it's netted out over a year through power purchase agreements, right? And then Scope 3 is, we'll call it the big elephant in the room, is that, you know, a lot of that's the embodied carbon. It's upstream and then downstream, but you talk about upstream. So when you purchase your stuff for your data center, IT equipment being the biggest one, what's the embodied carbon associated with that purchased equipment? And there's a lot of work happening now for manufacturers like us and a lot of others to try to make that information available to everybody. Then another ISO standard, carbon usage effectiveness, to give you a ratio, and also offsets, how much offsets are you using? And then the last one is a lot of leading players are actually looking at matching their purchase of renewable energy to their hour-by-hour consumption. So that's not super easy to net it out over a year, but to actually do it hour by hour is interesting, and we should all be striving for that. Okay, water, probably one of the top sustainability topics, I think, in the last year and a half. Total site water use, total source water use, so how much water is being used at the generation site, especially if it's thermoelectric generation. And then you can get your WUE, and there's different categories of WUE. Is it potable water, other kind of water? Do you take into account the source? Water replenishment, and then a real leading one is water use in the supply chain. So this is kind of like embodied carbon. So when you buy your thing for your data center, right, how much water was used to make that? And again, that information is starting to become more transparent. I'll go through here. So the waste category, just how much do you generate? And we broke out e-waste and battery waste because those are actually consumables, right? If you think about e-waste and what are you doing with that? So you want zero waste to landfill is your goal for all of these. And a diversion rate just puts it into a ratio so you can do some comparisons. And the last but not least, luckily the data center segment is not a monster land use like mining or other industries, but there still is an impact. So there's different ways you can take a look at that. And if you think of HPC and the densification that's happening, I think that's a good thing because now we can kind of shrink our footprint on what we're doing. Noise is another thing, and mean species abundance is a little-known metric that's kind of developed over in Europe and France that kind of looks at the impact that you have on local ecosystem of different species there. So I wanted to kind of start off with our definition of what we think environmental sustainability is and what you should be measuring. And I'll leave it at that.
All right,
Great.
perfect.
Yep.
All right, Andrew. Next up is Andrew Chien.
So they're all on deck
that
here?
should be next, yeah.
I don't think so.
No? Oh, good grief.
Nick's slides are up. Nick, should we just have Nick go?
Yeah, sorry. My bad.
I can present Nick's slides. He'll do a much better job.
All right. Wanted to take a perspective this morning on the carbon footprint of generative AI. Everybody's been talking about ChatGPT and the various other foundational models and large language models that are now ramping up. And I wanted to give a perspective on that this morning and get you guys to think about how maybe we could address and do it in a more sustainable way. First off, it's interesting to look at this chart, which is it's a log chart, and it shows you how, in terms of FLOPS intensity, we've gone from the first stage of machine learning to the deep learning stage to now all the LLMs and the big foundational models that are very compute intensive, to the point that some of them, require the equivalent of 1 week of frontier of the entire system to train. And we're on a trajectory that it's actually going beyond that. And that's just for training them, right? That's not even for inference. So the whole inference, although the inference workload is lighter, it's actually much broader in terms of how dispersed it is and overall energy consumption. So think about this as the training part is only the tip of the iceberg for any foundational model. All the inference will follow and will actually consume even more energy. So mapping that out, GPT-3, right? That's behind ChatGPT. That's from the Patterson paper. Took 1287 megawatt hours of electricity and generated 552 tons of carbon dioxide. That's training it once. Now, all those foundational models are trained multiple times these days. So that's significant. And so the 552 tons of carbon dioxide there came from the embedded carbon that came from that electrical grid on which that neural network was trained. So just as a reminder for you guys, the carbon intensity of electricity generation looks something like that. Fortunately, we don't see Thank God we don't see those clean coal ads anymore on TV, because there's no such thing as clean coal, okay? Can we, I remember I've said that 5 years ago, and let's just be honest here. So I think this is a fundamental driving factor, and we have to start looking at ways to locate our data centers on clean grids, right? Having the data center located in our backyard because we're a government entity or for whatever reason, because we like to hug our servers because we're nerds, right? And we sure like to have our servers right next to us, is actually not the sustainable thing to do. Because most likely, you can't be on a grid, even if you're on a grid that's got basically an ability to pay for renewable electricity and to pay a little bit more per kilowatt hour so you get more of the renewable mix. What you end up doing when you're doing that is actually adding load on a grid that's already has got a lot of high carbon content electricity generation. And typically, the renewables are not the fastest one any electrical producer can ramp. Coal, they can ramp pretty fast. So all you're doing is, even if you're paying more, right, per kilowatt hour, there's no such thing as electron routing. So I would just hope that as a community, as an industry, we stop trying to greenify, the electrons. Because again, you can't route green electrons on a grid. So if you consume more on a grid that's got high carbon content, really what you're doing is you're not helping at all. So I think as an industry, and when I say as an industry, it's beyond HPC. It goes into AI, hyperscalers, and all of that. We really need to look at places to locate our data centers that have sustainable, renewable power grids. One example of that is in Quebec. The power grid is powered by it used to be like 98% hydroelectrical. Now they've been deploying wind power. It's still 100% renewable. If you go on the Hydro-Quebec website, they'll tell you it's 99.5 because there's some remote sites that needs on islands and up north that needs diesel generators. But from basically what's tappable in from a capacity perspective, it's 100% renewable grid. These guys are building a site that's over 100 megawatts. It's got free cooling year-round, and they're doing it the right way because they're not using swamp coolers. They're using V-shaped dry coolers, and they can have evaporative assist if it's absolutely needed. But for the most of the time, right, they're using free cooling without any water use. Well, what's most interesting is that they've actually secured the land, and it was agricultural land that's right next to them. And they've bought the land around the data centers, and they're co-locating with greenhouses. And I've been in the sustainability kind of for HPC groups for over a decade, and we've been looking at that. Remember sub-projects in the Netherlands back then and everything. And we have to really double down on projects like that, because when you're doing that, now you can do heat recapture. So for my last slide, I'm going to do a little math exercise with you guys. How many tomatoes, right, in greenhouses can ChatGPT grow? We'll do math, and you'll see it's actually quite an impressive number. So a typical 500 square meter greenhouse in Quebec, Canada, will have about 5,500 climate hours that will be below 10 degrees C. And I could have taken 14 degrees C. I took 10. So a lot of those are kind of estimates, but we're in the ballpark, right? That's about 1,000 gigajoules per heating season. On the other side, right, on the input side, ChatGPT training took 1287 megawatt hour. That's the equivalent of 4,633 gigajoules, or the equivalent or 4.6 greenhouse energy requirement for a year, for an entire year. Now how does that map out? What's really before I give you the final answer, what's really cool is that in addition to being on a 100% renewable grid, basically that has very low carbon content per electron, so you're already saving the 552 tons from your electrical feed. But also, most greenhouses, even in Quebec, are heated by natural gas. So if you're recovering the heat from a liquid-cooled supercomputer, you're going to get it out at 35 C roughly. Sorry for Americans. That presentation is in the international units. I have a prof that used to say, scientist talks in Kelvin, engineers talks in Celsius, and we don't talk about Fahrenheit. But okay, so the principle works this way. You're going to get 35C out from your computer. For doing hydronic heating with basically with thin slab and a water glycol loop, really you're going to have a set point around 27C. So your water coming out of your supercomputer doesn't have to be in the 50s, the 60s, if you're piped right next to it, and you actually can pipe the warm water to heat your greenhouse basically in the concrete slab in the greenhouse. So what happens when you're doing that is that not only you're doing the sustainable thing and not consuming carbon-loaded electrons on the input side, but you're also offsetting the gas that would be otherwise used to heat that greenhouse. And that's how the math works. So basically at 70% combustion efficiency, which is kind of what people use usually, you're gonna be saving 85 tons of CO2 equivalent per greenhouse annually, or about 400 tons of CO2. So you add that up, that's 85 cars for that, add up to the other one. Basically, you're saving about 200 cars worth of carbon footprint, and that's for training ChatGPT once. So how many tomatoes did that work? So believe it or not, but a greenhouse can produce 75 kilograms per square meter per year. I did not believe that. And oh, by the way, some of the best ones can actually go up to 95 kilos of tomatoes per square meter. So I took the lower number there. About 85% of the greenhouse square footage is used for production. So 4.6 greenhouses times 500 square meter times 85% of that surface, you got 1969 production square meter times 75 kilos. That's about 147,000 kilos per year. How many tomatoes is that? So that picture there is precisely 1 kilogram of tomato. I can tell you when I went to the grocery store with my tomatoes and I was on the balance there and I'm like, I want 1 kilogram of tomato. The guy was looking at me kind of weird. And I ended up swapping some tomatoes and he's like, okay, you got it. I'm like, thank you very much. I needed that for my picture. So it nets out to 1 million tomatoes for training ChatGPT once. So I kind of use an illustrative example to get you guys to it's kind of funny, but the math actually works, and that's the kind of mindset I think we need to get into as a community, not just about no water use and limiting the electricity use, but also really trying to tie that into a broader ecosystem. Thank you. Thanks.
All right, well, that may be the facto to the meeting right there, tomato production. Next up is Andrew Chien from the University of Chicago.
Oh, okay.
Yeah.
Sorry, let me turn off the loop here. Make sure we don't get any feedback. We have some minor AV challenges. That's why we're doing this laptop swap. Which of these things should I connect? There's like 3. This one? Mac, HDMI? Okay. Hopefully that'll work. Can you guys hear me? Excellent. So, great talk. I have to follow Nick here. So probably many of you know me, that for years I've been an advocate for environmental sustainability for cloud, looking at various measures like how to make your data centers behave better as citizens in the power grid. For example, your constant load data centers are retarding carbonization of the grid. So, you're not neutral, you're actually on the side of slowing the grid's ability to decarbonize itself. Another thing that's worth mentioning is that I think that the very aggressive standards that the cloud industry is pushing itself for, whether they be offset carbon-free or 24/7 matching, they're not ambitious enough. In fact, I think this HPC community should challenge itself to do better because, the realities of things like 24/7 matching are that you're appropriating the green energy in the grid, and you really probably don't own it, right? I mean, you're disenfranchising all the other power users in the grid to not have any stake in that renewable energy that you're purchasing. And this has already happened in a couple of places in Europe where the local citizens were very mad about this kind of accounting. I think we have the opportunity in HPC because our workloads are more flexible to do even better than that. So with that, I'm going to move on and talk about a slightly different kind of sustainability. Oops, what is that? Where's my mouse? Okay. I'm not going to talk so much about environmental sustainability. I'm going to talk about something different. So I've been trying to figure out how we preserve the sustainability of supercomputing progress. That is, how do we keep our, if you will, way of life in the HPC community going forward? So Dan spoke to some of these issues earlier. We did a projection back in 2016. I'm not going to claim this is original to us. Many have done such projections. But if you look at the progress we've been making over the past several decades, one way to fit the curve is something like 200x performance every 5 years, which has been, in recent years, attached to a corresponding 3x power increase for the largest systems. So, what's going on right now is, we had Fugaku at about 20 megawatts, Frontier, super nice energy efficient system, similar scale of power. Aurora is coming online at 55 or maybe 60 megawatts, depending on who you ask. The projections lead you to believe that by 2027, a leadership system will be 120 megawatts, and a shocking number by 2032 will be 300 megawatts, right? So this is what potentially we're getting, and some people think, it's going to be worse because silicon technology progress is slowing even faster than this. But it looks ominous no matter what. So I've been trying to figure out actually how we can sustain the growth of HPC computing power. And I think of it as three things. So the road to the future, right, off in the distance, the sunny future, is both windy, of course windy, right, that's a pun there, and green, right? So that's how I think about it. So the real challenges in making this work is how do you make the economics work? So if you look at the TCO projection for a 2027 leadership class system, and you estimate the cost of power, you wind up with a TCO chart that looks something like this. You've got 40% CapEx for computing equipment, maybe 10% for physicals, depending on how efficient you are. And then you wind up with about 50% CapEx for power, right? And that arithmetic forces you into this realization that in order to lead, you're going to have to acquire hundreds of megawatts of power. And of course, none of us wants to harm the climate. So if you're going to acquire that much power, you better find a way to make that low carbon power as well as low price, right? If you're going to make the economics work. So we think that there are ways to make the economics work, that if you operate your data center dynamically with extreme variation by modern standards of capacity utilization, that you can shift the TCO balance back to be more like a 2018 TCO balance, that you can dramatically reduce the cost of power and, fortunately, at the same time, reduce the carbon content of that power as well. So this is, I think, consistent with many of the things that have already been said. So we believe in order to sustain HPC leadership, and by the way, this applies to all the smaller scale systems as well, but of course it's most vivid for the larger scale systems. You need to acquire large quantities of power, low cost and green, that you need to build dynamic data centers and systems that are TCO efficient in exploiting variable capacity. Dynamic ranges as large as 10% to 130% capacity. That's heretical. If you talk to a data center operator today and you say that to them, they'll kick you right out the door. They say, get out of here. But I think that's where we're going. And then third, because our HPC workloads are often not online, very flexible, that we need to operate flexibly with workloads time and location, as was mentioned earlier, adapting to power pricing and carbon for sustainability. I gave a much longer talk about this at the Sustainable HPC workshop 2 days ago, which I think is also online and available to you guys, so I don't have time to go into that now. But let me just give you one highlight for this. The highlight for this is we've been working with the folks at RIKEN in Japan to try and understand, could these ideas be applied to a very challenging environment, which is the electric power grid in Japan? So we've been calling this study Fugaku Next. And our projections suggest that if we employ these kinds of techniques, that for a 2030 to 2040 operational window, which is not unrealistic for the next system they would build, it's possible these techniques could deliver a 90% reduction in power cost and a 40% reduction in carbon emissions, on top of the grid already improving itself 30% in that time period. So that would allow a 120 megawatt supercomputing system to have a CapEx-OpEx balance as shown here on the right, similar to a 2018 HPC kind of balance. Another way to think about it is that this is what is likely to enable Fugaku Next to be a larger computer system than Fugaku today. Well, I don't mean enable it to give more, exaflops. Of course it's going to give more exaflops. I mean larger in terms of power consumption, right? So it's possible if you are constrained not just on the power side, but on the carbon footprint side, and you're told you have to operate that future system within the same carbon footprint as Fugaku 2022, then these techniques would allow you to build a system that's 2 times larger, that is, consume 2 times as much power. If a more realistic view is you're going to be told you have to operate within the carbon footprint of 2022, scaled down with the improvement of the grid, because that's what we're going to ask everyone else in society to do, right? Then this would allow you to build a 1.5x larger system scaled with power grid improvement, and the projections are kind of shown to the right. So I think a couple of observations. First, everyone thinks power is the problem, but it looks to me like carbon is the tougher constraint. Supercomputers of all sizes will face these challenges, big and small, because after all, you're going to be measured within the context of what you're doing. So with that, I'm going to sit down. Thank you.
Sorry?
Zero procurement by 2050 is another one that I think about for HPC and for computing. So those are just some of the goals, but I'm happy to talk more about like specific regulations on the federal side. And then, yeah, my perspective is kind of from sustainability as a whole and for our particular campus.
Perfect. All right, so we have one online question, which I'll start with, which is, does the tomato anecdote mean that we can only train AI during the winter? And please come up to the microphone to ask questions.
So the question might sound funny, but it's actually, if you think about it, it's actually quite relevant. The way you'd want to think about it is that there's 2 hemispheres on the planet, and when there's summer in the northern hemisphere, there's winter in the southern hemisphere. And I think the way to think about it is that inference and some of the other workloads are very latency sensitive, and they kind of need to be co-located with the populations, and they're somewhat harder to move. But large-scale training jobs are not some kind of a very latency sensitive, need to be connected to the side of consumption. So when you think about this, those large-scale workloads should actually get relocated or pushed out to where it is most sustainable to compute them at any given time during a year period. And I think that's a way of thinking about it. So yeah, maybe it's only during winter, and you follow winter as you with the seasons.
Yeah, I think several.
Go ahead. If I could just chip in on that, I think a lot of people are aware that there's variability in power grids on a daily basis, perhaps if you have solar or changing load or the like. But there's actually very substantial variability on a seasonal basis in many places around the world. So even seasonal shifting is a useful thing.
Anybody else want to comment on that? I'll just note that, many of us have worked in environments that have artificial constraints. That notion that the machine has to be close to us, and part of what several of our panelists are noting is, and that does not have to be true. And certainly if you look at hyperscalers, yes, there are placements of facilities based on geography, as Andrew just noted, but the cost of energy, the environmental footprint, those are part of the decision processes about where facilities get placed. Yes, please introduce yourself and fire away.
I'm Patrick Jackson from Los Alamos National Laboratory. Hey, Jenna. My question is actually kind of 2 parts. First, as we move into the sustainability world with data from transmission to distribution, how are we working with the actual vendors that we can get? A lot of systems, once you move down to distribution, are proprietary. How do we get that so that we can cross-talk between PUE, WE, and CUE so that we can get the information needed to pass back up? I know we're doing it at the transmission level, but we're working with the data centers. That information is important on how we change our grid. Is there any movement to try to stop the proprietary stuff and maybe move a cross collaboration between vendors for information?
Just to make sure I understand, is this a little bit of the kind of the divide between IT and facilities type of?
It's divide between policy and technology. A lot of technology is becoming laser focused on just that technology. Unfortunately, the information we need is cross between systems. So how do we get that, and how do we move forward?
Okay, I'll do just a very quick and pass it off. I do know that there's been more talk among vendors and standards committees about data sharing, and more importantly, I think, into the previous topic of understanding the IT workloads and how that interacts with the facility and the grid altogether. And so I think we're on the cusp of stuff happening, but I want to turn it over for maybe a more precise answer.
Maybe I can comment on some of the things we did at Oak Ridge, tying in the computer side, the IT side, with basically you're coming from a facility side where you have a BMS or building management system that speaks whatever protocol, and that's what you see as a facilities operator. And a lot of time there's kind of a wall between that and the IT side, right? And I think that's where your question's at. So on Frontier, for instance, we've coded a lot of, they're not exports, they're basically live hooks that are pushing into the BMS, the data that's being produced and monitored on the power and the water and all of that at the IT system level. So this way we're able to foresee, like, for instance, when you start a Linpack job on that system and you go from idle, you hit return, and then the building shakes or almost, because you're ramping up from like 7 to over 20 megawatts. And there's nothing on Earth that actually swings a power grid like that as much, which is quite a kick for a nerd, by the way. But but when you do that, right, you want to have facilities typically have a response curve that's much, much slower than the computer. So, and that's why it's really important to couple the two. So as you're doing stuff on the IT side, the nodes and then the CDUs will see the heat load, and then all of that gets up leveled, but ahead of time, then your cooling towers and your cooling equipment see it. So I think there's work that's being done there. It's kind of still manual. I think from standards body and everything, we have room to improve there to connect the BMS with the IT. But it's been done. It can be done. It's a matter of pushing it.
Yeah, sorry. I'm going to interject here for 1 minute because I know none of you know this, but there's a BOF tonight at 5:15 to 6:45 on the Power API and other software activities. And it's specifically going to talk about the intersection between the facility and the HPC system. So unified software power management.
So that's terrific. Thanks, Natalie. So let me jump on top of that. So I think the two gentlemen have made very good points that it's important to be able to integrate that information and control across those different parts of the system. I'm all in favor of that. I'm going to raise an objection to the notion that the goal is to optimize PUE. PUE has been really good for the industry, driving energy efficiency and driving what was perceived as waste of power, but I don't think it's the right thing to optimize anymore. And it doesn't make sense to optimize it in a time-independent fashion when power price is varying by as much as 10x or more from one period of time to another, so it doesn't correspond to cost optimization. And if carbon is varying by as much as 10x or more at different times of day, optimizing PUE doesn't correspond to carbon optimization. So I think, we need to get beyond PUE. I'm not saying it's a bad thing, but we need to have richer metrics that actually take into account these other dynamics.
Okay, I want to respond to that. I agree with you, but I don't think, Rob, and maybe let's drive some debate here. I don't think we need 26 metrics. I think that becomes way too complicated. I think we need one metric.
Start with 6.
Well, how about one? And it would be drive to zero. Basically zero, like net zero. Like you build net zero buildings, right? What's the equivalent of net zero for a supercomputer? Zero water consumption, and then zero net greenhouse emissions, right?
True. So I'll say I don't disagree, which is a little bit different than saying I agree, I guess, right? I hate it when people say that. So yeah, I know 26 is a lot, but they do help you focus a little bit on what the actions are to take. If I say, get to net zero, what do you start with, right? So those might help get there, but yeah.
Good
All
debate.
right, there's an online, maybe as much as a comment as a question, and then I'll come to you over there. And so the comment in the question is, there's no appetite for the projected OpEx at $1 million per megawatt year. How will the industry move from to something significantly less? And I will say this is an issue depending on, it relates to the previous question because OpEx and CapEx often come from different budgets and there are different political constraints on how they can be spent. But that issue of the price of power is a real one. Anyone want to comment on that? So basically, the comment was, and I'll quote it again, there's no appetite for the projected OpEx at $1 million per megawatt year. Basically, they're saying the cost of energy is prohibiting us from building larger systems, I think is the gist of the point.
Oh, well, that's exactly what I was trying to get at. I mean, if you look at the distribution of power prices for wholesale markets, the price of power varies widely in most power markets. And in many power markets, you can get 90% reduction in your power costs and average price per megawatt hour if you are willing to sacrifice some small percentage of unavailability. So you're paying a very, very high price for reliability. Now, this is fundamental, in my opinion, and it's the product of volatile generation in the grid. You know, everywhere in the world, people are pushing for higher and higher fractions of volatile generation. So there's every indication it's going to get more extreme if we're going to use market methods to organize that matching. So I don't think if you're willing to give up, if you're willing to give up a little bit of availability, you can dramatically reduce your costs to maybe $100,000 per megawatt per year. It really depends on where you are, of course.
Hello, Colton Hoppen-Nichols, Cyber Infrastructure Director at Montana State University. I happen to be from a public higher ed institution that in some ways has a lot going for us. We have a primarily hydroelectric energy grid. We also happen to be in a cold climate with a heat transfer system between many of our buildings. At the same time, with all of that, we're in a very budget constrained public university. And it's a big challenge to try to get funding from those who are making decisions between things like efficiency improvements for heat recovery from a data center, for example, versus building classrooms for students. So do you have any advice for how you talk to decision makers in that kind of a public sector in terms of getting support for some of these very capital-heavy initiatives that often can't be funded out of the kinds of grants that pay for computational infrastructure?
I'll maybe start an answer, and I'm sure others will pile on. I think we need to break the whole big wall of divide between CapEx and OpEx funding. Once you start doing that in your procurement, then you start doing a lot smarter things. Because then if it all gets pooled and as a project, you say, okay, it's overall TCO over the 5 years lifetime operation of that system, then you actually get to fund with some of the CapEx, the energy recovery and the energy efficiency. For as long as procurements and funding agencies will separate CapEx and OpEx, it makes it really hard to do the right thing. And I think that's the first thing this community needs to tackle. Some sites, like LRZ, for instance, Germany, are really good at that, have shifted that paradigm, I don't know, at least maybe a decade ago, but it's still not largely adopted in the community.
It's a perversity of many budget models, unfortunately, and changing it is key to. We often are trying to solve an over-constrained problem, is maybe the mathematical way to say it. Yes.
Yeah, and I would say we obviously deal with this all the time. People are like, I don't care about sustainability. I want to make sure that my whatever runs, or that we, make whatever mission thing that we need to do. And classrooms are kind of similar, right, if you're in a school setting. So I would say our biggest thing, and my colleagues always remind me of this, is trying to say, what is something else that you're going to get them besides energy efficiency? Are you going to get them reliability in your system? Are you going to, maybe you make some really awesome data center that you're going to bring more grants or bring more people in. I think that's kind of how I always try to look at it, is what else can I give someone besides just energy efficiency? Because if you're in a place that has all that awesome stuff and you already have enough power and water and whatever else, like just saving a little bit probably won't make that much of a difference. So finding that other angle.
All right.
Thank you.
I heard a lot, oh, sorry, Dan Philippi, Navic Pacific. I think I heard a lot about generation. What I'm curious about is what role do we think that technologies for things like advanced power management can help us reduce our overall demand? And by doing so, how do we, I guess, how do we incentivize the technology vendors themselves to actually produce products that incorporate these APM tools inside of them to really make it worthwhile, so that way we can get a reduced demand level, but keep our peak performance when it's needed?
Yeah, I missed a little bit in the middle. Can you just restate the question on tools?
Sure. So when it comes to reducing our demand, what role does advanced power management play in light of all the power generation? How do we reduce our overall demand, but then still maintain our peak performance for when we need to do the modeling and we need to do the simulations?
Yeah. So I'll give you a simple example, at least from us as a vendor perspective. So our goals with regards to carbon, so Schneider Electric's goal is also downstream scope 3, right? So the use of our products is, uses electricity. So a simple thing we did, so we have a UPS product and it has an eco mode. Typically people don't turn it on just because, they might be scared of it. We now have enabled eco mode and have, when it's commissioned, turn it on, tell them on. And so now our use rates of that. So we're saving like 3% efficiency just by a process change during the commissioning. So at least from an incentivization of a vendor perspective, we do track our downstream scope 3 emissions. And so it's important for us to put in any type of tools or software to try to reduce that overall. And there's a lot more to say on a dynamic perspective, I think.
So at HP, we do have advanced power management as part of our systems and our system management. What's important to think about with that, right, is that from a procurement and even from an acceptance process of the systems, that might mean that you can't run your LENPAC run your system this summer, right? Because if we're capping and we want to keep the system cool, and then you're on dry coolers and you don't have the cooler water during the warmer months, then it's going to introduce some limitations. And I think that's the way to think about it. So your question's spot on. We need to have those capabilities on the systems, but also from an operations perspective, I think we need to start also having that flexibility and sure, capping the system power usage, but that also means making consumption, making trade-offs on the consumption depending on the season, and maybe not running the highest workloads during the hottest days. And a lot of users, unfortunately, are not ready for that, and that's a cultural change we need to drive.
Thanks.
Let me just add on that the positive side of that. So while you may be constrained at certain hot days or certain seasons of the year where there's more competitive load on the grid, the trade should be that you'll have 1.2 times, 1.5 times the capacity in compute hours or whatever units you want to use at some other time in the year, right? There has to be a trade and an upside, so I think that's what it is.
Hi, Ada Gavrilovska, Georgia Tech. So some of the techniques that kind of came up, shifting ChatGPT training to another hemisphere, they imply increasing data movement, increasing capacity, memory storage, and there wasn't kind of an explicit conversation about the importance of that data management aspect, data movement aspect when it comes to kind of net zero goal. Is it a problem? Is it significant? Is it something we need to worry about? And what's being done? Any comments?
I think it's important. I think one of the reasons it hasn't got as much attention, it's a little bit harder to measure, and it's not centralized in terms of a particular vendor or a particular constituency maybe having sole responsibility. But you are starting to see a lot of pressure on ISPs in Europe, for example, to report on sustainability kinds of considerations. I think for some of the largest training activities, in some cases the data is highly replicated. So it's not the case that it's just in one place and you're necessarily moving it around because you're spreading or orchestrating the training. But it's a complicated thing to analyze, and I think it's super important. Yeah.
It's also true that we talk about networking bandwidth, and there are faster ways to ship data. It's still true that FedEx is the fastest broadband delivery mechanism. Yeah, so you have to think about that. And this is related to a question that's in the online, which is, it's about, as we think about moving to carbon neutrality by choose your date, depending on the political winds of the day, how do we create procurement incentives that incent all of us to do the right thing? In some sense, this is a version of stop me before I kill again question. What do we do that creates an environment where the incentives are aligned with achieving this goal?
I don't know if this is an incentive, but I think it's worth something pointing out to this very scientifically oriented community. There was a paper published in Science this summer that did a study of offsets and the offset markets in the world. So if you're thinking offsets are going to be a substantial part of your story, I'd recommend you read that paper. That paper suggested that as much as 95% of offset credits are not material, that they don't correspond to any real reduction in carbon emissions. And this study covered about 2/3 of the sourced offsets in the world.
And I would just add to that, like us as consumers or us as purchasers of, different equipment, or like that other question about vendors and like getting the right systems. I mean, we're the ones that need to say, like, we want this, we want net zero, materials from our vendors. We want to talk about scope 3 emissions and embodied carbon within our things that we purchase. I think it's a really big thing that we just have to push as a community and say, this is something important to us, and it's okay for us to spend a little extra to get what we need.
As the system vendor here, I would just say opening up the scope of the RFPs is the way to go. I talked about OpEx, CapEx, and bringing those together. But then it's also integrating, like, okay, you get bonus points for an award for no water utilization, because your system is able to, instead of requiring a swamp cooler or chillers, having a liquid cool system, it's able to be cooled by warm water cooling. And in that location can basically be done with dry coolers year round. I've seen very little procurements, and I've been doing that for quite some years, that actually award based on criteria like that. And I think this is where it needs to change and really embody and have a whole more holistic view of the procurement, the operation of the system than just pure flops per dollars, or the classical ways we've seen it over and over.
No. Yeah, go ahead.
Short thing. I love what Nick just said. He's saying, let us help solve this problem. Let us help align these incentives. You just need to open up the box a little bit. That's great.
And that goes back to what I said at the outset. I think being clear about where we're drawing the defining bounding box to include these issues is a piece of the story as well. Yes.
Hello, everyone. My name is Tobias Mann with the Register. My question relates to water consumption. Over the last year, we've seen several new builds of data centers move away from evaporative coolers, particularly in arid climates. My question relates to location as well. Is that move away from evaporative cooling in the interest of reducing water consumption always necessary? I happen to hail from Minnesota, the land of 1,000 lakes, where water is very plentiful. So I'm curious to hear whether or not reducing water consumption is always necessary, or if it's a location by location kind of situation.
All right. A lot of companies and some of the major public do have a goal of zero water use, period, no matter what. And I think that should be viewed, I think that should be a goal no matter what. And as the grid gets greener and there's more renewables, then the trade-off of water use at the power plant versus water use on site becomes less of an issue. The other thing I'll say is there's locations that today might seem like no problem with water, but the variability in dry areas that we're seeing, it could change in 5 years. So you design a cooling system for evaporative because you got tons of water. 5 years later, you don't have tons of water, and then you're screwed. So I think it's prudent to err on the side of using little to no, or the flexibility to change it.
So I happen to live next to the world's largest freshwater bodies in Chicago, in the world. And I was astonished to discover that there's huge local concern about water use and availability of freshwater supply. Any new large community or any new large factory or facility that's built, not just computing, has scrutiny, has to apply for water use access and so on. So I think it's a function of the modern societal sensibility about this, not actually the absolute quantity of water that we might see when we drive around.
So this is one of my pet peeve. What's the drive to PUE, and it kind of relates to some of what Andrew was saying earlier, really drove bad behavior. Because some people build data centers, some hyperscalers, I'm not going to name them, but build large data centers, Arizona, New Mexico, and very dry countries. You build data centers there, you use evaporative cooling, you're going to have a spectacular PUE. However, you're going to consume a resource that's way more important in that community than optimizing for a few percent on the energy consumption. So people doing that, I think that's criminal. I think they should be jailed for doing that. No data center using evaporative cooling should be allowed in those locations. This should not be allowed. And when you go to locations that are, even on locations that have plenty of humidity and plenty of water, then evaporative cooling is not as efficient because obviously the air is more humid. So the push is very simple. Just drive from your vendors a requirement to have a system that can be cooled with dry coolers in the location. That's it. And we can do that today with water-cooled systems. And there's no reason to still build large data centers that are using evaporative cooling. That should just be banned. So sorry for being so passionate about that one.
Well, you put that opinion out there. Good.
Well, being the person from New Mexico who has a type of data center like that. Like I said, one of the really big things that I'm proud of, and I wasn't there when we built it, but like our data center uses pretty much 100% reclaimed water. And I think that's another option if you are in a situation where you have this data center and you need it to keep running. I mean, we have a very really cool system that, like I said, takes effluent from our wastewater treatment plant, treats it, and we pump it back to our supercomputer, and we get to use that water, which is like a great story, and we don't use any potable water for that particular cooling method. But obviously there's always energy-water nexus, which we all know about, and it also depends on your grid. If you can't get enough power to wherever you're going, that's another thing. So it's I think it's very dependent on where you are, but I care a lot about water, so I err on the water side too, of saving water instead of energy.
So for example, what we are doing with the Lumi, we are not using water at all for the cooling. So we are located so high in the north that our climate is cold enough to operate with the dry coolers year round. So this is why people should really think where they locate their data centers.
Yes.
Sir, Jeff Hansen from HPE. I'd like to make 2 points. In addition to Natalie's bid for the BOF that's today, there's a BOF on Thursday afternoon, because if you're going to get, okay, I need to take all this data and do something with it, this is operational data analytics. Come see us. The second point is one that I think Norm would have made if he was standing up here, which is you're over-specifying your stranded power. So this is another opportunity for policy and technology need to come together. What is the plan for allowing data centers to be built where there is no more stranded power?
We're still living in I think a hangover of data center designs based upon the financial industry of the 1980s and 1990s, right, with regards to 7x24 availability and all that stuff. So, and it is tough, right, for the engineering community broad to try to get out of that and understand that there might be levels below that that are going to be okay. But yeah, understanding strata capacity, not only in your power system, but your cooling system, and then space would be third, I think is going to be important. And really rethink redundancy and time shifting of availability also.
+1 for all that.
So there's another question online, which is, how should we take the carbon emissions associated with manufacturing of IT equipment into account?
So that one, I don't think a ton of people have quite figured out how to account for it yet, but that is going to be with all our Scope 3 emissions and how we manage all of that. I'd say like our GFE equipment, we haven't really got regulations on that, so that's something that we're kind of trying to figure out. I don't know if some of the suppliers want to add what they're doing.
Yeah, we use you know, the EPDs, environmental product disclosures, or you know, there's another name we use, will specify all the stuff, the amount of carbon that was, you know, water, other minerals, and we don't have it for all our products, but it's a huge internal effort to try to get that, and so that's forcing us to obviously get our factories on renewable energy and all that other stuff. So it's happening, and it's just a ton of work, and I know a lot of the vendors are doing the same thing.
So to me, that question is an interesting one. I think of the Scope 3 as being a mechanism intended to force accountability over a broad scope of, you know, supply chain and downstream use on corporate entities or organizations that are non-corporate, nonprofits, everybody really, to prevent sort of outsourcing and hiding of these kinds of things. That's one view of it. The other view of it would be it's an attempt to use sunlight, if you will, to give incentive, right? So, you know, to Nick's comment about, you know, procurement structures or what messages you give to your suppliers and so on, I think it's super important to use the availability of that data as a way to either financially reward them with higher payments, if that's appropriate, but also to encourage them to improve in the future.
I think there's another end that falls on the consumer side, and I use consumer in the big sense, including large procurers, is what do you do after the equipment reaches end of life? That's another big issue that affects carbon footprint, and that falls, you know, in both on the procurers, but also on how do you recycle the components.
Well, I think, and on that, right, if you think about full life cycle, well, it's with longer life cycle, it actually helps your case. So the fact that the end of Dennard scaling, as you were showing in your intro slides, shows that the chips are actually not improving as fast per unit of energy and all of that. Well, it probably means that we're going to use our computers for a longer time, which means that your end to cradle to grave life cycle is longer. So we're not used to that, but instead of using a system for 4 years, maybe you're using it for 8 years. And the hyperscalers are already doing that. So, and because they're always kind of tearing down the older chips. And I don't know, Dan, if you can comment on that, but I know many platforms will stretch out all the way out to 8 years and sometimes more.
Yeah, that's absolutely right.
My question was actually related. I'm from the University of Wyoming, and I recently had a conversation that was about the sustainability of training large models. And my question was, like, what is the environmental impact? And the answer I got was naive and unsatisfying. It was, well, we just use AI to solve the fusion problem, and then we use fusion energy.
I think the short answer is it's god-awful, but...
Yeah, so I guess, but that question kind of ignores another aspect of sustainability, which is sort of what you talked about, material sustainability. So what are your thoughts on the sustainability of the materials used in constructing these sites, in the systems themselves, and the life cycle of these materials? Like, what are your thoughts on sort of shifting that in the future, or just in general?
Anyone want to comment on that?
We've been very guilty as a community to do rip and replace on our system builds. Like the whole thing, right? A new system comes in, it's the whole system, the whole previous system gets taken out, and then it's a whole overhaul, and we have to replumb the whole thing and everything. I hope over time we have a way to maybe get smarter about this and have some kind of a, I hate to say OCP because we're kind of have different requirements than the OCP community, but the equivalent of an OCP for HPC, where maybe we could have reusable infrastructure, reusable, all of the plumbing, the piping, the electrical distribution, and then you change the sleds, right, as you're changing technologies, and you have something more flexible. That's a hope. That's not a commitment from my company yet. I hope we get there soon. But that's the kind of thing I think we should look at.
Yeah, and from a site perspective, people, green concrete's a thing, can you, instead of greenfield, can you take a brownfield, turn that into a data center? So I think a lot of these things are being discussed now that weren't discussed a couple of years ago with regards to that. And used equipment, so, can you take your stuff, get it recycled so it gets a second life with somebody else? Now, you don't get carbon credits for that right now, but at least the people who get it, get a very, very, very low carbon thing because it's second life.
I would say too, when we're building facilities, like really looking at kind of the latest technology or, how do you make that building net zero? And like, I'd say right now for us, it's hard to renovate what we currently have, or it's a huge cost to try to fix something that was originally broken. So like adding that in from the onset and not trying to value engineer it out, I think is another really big thing from like the facility perspective.
I'll just add an old Microsoft story from my time there. It was a realization, one, that we did not, which the industry has embraced, that we didn't need to cool computer rooms to polar bear environments, right? That was a big cultural change among us. I used to wear a parka when I worked in the computer room, and that world has passed. But also the notion that there are trade-offs about, just as there are trade-offs about when you compute, there are trade-offs about the reliability of systems versus the energy footprint you can make as well in terms of failure modes in different kinds of environments. And that's a different kind of bounding box calculation. But any other, yes?
Yeah, I have one comment about the greenfield versus brownfield solution. As we did with the Lumi, we used the old paper machine building where we put our data center, so we did estimate that we were able to reduce about 80% of the CO2 emissions for the data center building using this old building instead of building all new.
I mean, we're all guilty too. How many of us have a dead computer closet filled with old smartphones, power adapters, old PCs and Macs? I mean, this is a cultural issue at large scale. Yes.
Hello. You just mentioned Microsoft. I was just reading an article. I guess they're experimenting or attempting to build a data center underwater off the coast of Scotland. What's the practicality or the future for data centers under large bodies of naturally cold water?
Sure. Yeah, so I know those people. They're some old friends of mine. I mean, it's been part of a long effort at Microsoft trying to look at alternative cooling strategies. An anecdotal aside, Bellotti at Microsoft actually put some old servers in a tent in Seattle for a winter, with no environmental protection at all, and they just kept running. And this was the kind of anecdotal story that drove people to think we don't have to have such tight environmental controls as we had all been inculcated to believe. And so some of this is just pushing the envelope to try to, explore some different ideas. I won't speak for Microsoft and say I believe they're going to build an underwater data center. I think that's unlikely, but it's trying to explore the range of possibilities. And obviously, there's a lot of water in the ocean, and so ambient cooling sort of comes for free, or sort of free.
I once got a question about that project. Very, very cool project from a technology point of view, and my oceanographer friends went batshit.
Yeah.
About the disruption of the environment.
Maybe a better way to do it. There's a site, I don't know how public it is, but in Norway, that's actually in a similar way, analogous way I explained about the greenhouses, where their heat reuse model is to warm up fish tanks for fish farming. And they already have the fish kind of ready to go, and it's going to go to Japan for the sushi market and all of that, and they're going to be producing like massive amounts, like 9,000 pounds of fish and fertilizer, because you also have the fish output. So, and also they have byproduct for that. So there's ways to actually think about how to do it in the right way.
So there's another online question, and I'll come over there. So let me just read it. Do you, and this is a direct quote, do you see the industry's drive to water and power reduction and carbon neutrality for company-specific ESG goals, inadvertently driving more greenwashing programs? What accountability should be enacted to curb this, and who should lead this?
Let me jump in on that. I think there's not much question that there's a lot of greenwashing going on in the corporate community. In fact, CEOs have started to call it out as being a little bit excessive. Now, I don't think it's very easy to get anything, to stop that. Obviously, that's a company presentation, market presentation, reputation kind of issue. But I think there are things that we can do actually to make the accountability more broad. For example, I think this practice of, through contracts, reallocating credit for carbon or carbon emissions is just rife with risks of abuse and, immaterial.
I'll be even stronger. They're indulgences for sin.
Okay, there you go. There you go. I wasn't going to go to that level about salvation, but maybe that's right. But there are simple things that could be done. For example, if companies were accounted on say, Scope 2 power carbon emissions based on the amount of power they consumed at the time it was consumed, simply the average carbon in the power that was in the grid, rather than some offset agreement that they had, that would go a long ways towards ensuring that their progress towards sustainability is attached to society's larger progress towards sustainability, which I think is the main issue.
Yeah.
Yeah, there's a lot more sensitivity to not greenwashing. But things like the Science-Based Targets Initiative also helps bring a little bit more transparency to it. So I think it's improving, and we'll see less, just lip service.
So I think we're improving. Let me give you an example. I won't quote names or whatever, or companies, but it was about a decade ago. There was a lot of very large data centers that were being built on coal-fired power grids by large organizations. And those organizations started to get a lot of pressure from Greenpeace and others. But they were getting power at sub 3 cents per kilowatt hour, sometimes on long-term contracts because, the whole coal industry and everything. So that there was good financials to make that. What happened there is that there was an initiative to actually have subsidized solar electricity. That was about 7x the per kilowatt hour price for anyone that would produce solar, would get the revenue from the local grid at much higher rates. So what happened is that the corporation ended up building a very large solar farm that was about 1/7 of their total power capacity, got Greenpeace off their back because they were producing solar power. But actually, that solar was heavily subsidized, and still from a net carbon consumption, since there's no electron routings, everybody can pretty much understand what happened there. So I think that was a decade ago. I think some of those things don't happen as much, I hope, because people are more, I think, see more clearly through some of those stunts.
So let me just sort of pile on for a little bit. So one way to think about that question is, what should you be doing, right? Or what can you do to be constructive? I think that that stuff progresses because of public opinion. That stuff progresses because there are exposés, if you will, done on current practices. That stuff progresses because there's public policies put in place that move the whole industry forward on a equal, right, and competitive kind of basis. So one of the challenges I think we face is I don't think you should expect that the companies or the industry is going to solve this problem by itself. Though there are many good-intentioned, and highly ethical people in industry, it's very difficult given the market competition and the profit incentives. So we need a strong advocacy by the general population. We need good public policy to support that progress. And then it'll be amazing the things that the industry is capable of.
Yes.
Yeah, so Aaron Anderson, National Renewable Energy Lab. Appreciate all the talks, and wanted to ask the question around metrics, and the question being, are we really missing an opportunity, particularly for this community, where we look at, I kind of look at the metrics and go, you've got traditional facilities metrics, you've got sustainability metrics, you're starting to blend those things. At the end of the day, does the researcher who's wanting to get the application through the system really care? And so should we really be looking at things like, carbon intensity of the job, energy intensity of the job, how do we expose that to the user community so that they can start to make the right decisions? And maybe we posit, tomatoes per job.
So you're asking, how do we push visibility
How
of
do we push
various costs down to the
visibility?
user base?
Those metrics are great, but at the end of the day, I show that to a researcher, they're not going to change their workflow.
Yeah, I think that it would be very reasonable to show the user how much they are generating CO2 emissions when they are running jobs in the system, and on the sites that are reusing the heat, we actually could show the users that how much they are reducing the CO2 emissions when they are running, for example, in the Lumi. So I think that energy efficiency should be visible also and energy usage for the users.
I'd second that. And I think there's a number of sites that are already doing this, giving feedback. Sometimes they give people just reporting. In some cases, they're giving them performance incentive, like I think the folks that we're working with, the RECON, we're talking about. In some cases, they give people priority access to the job queues, which is a big incentive for scientists, of course, under deadline. One could even have resource credits. I think Microsoft was doing resource credits a decade ago or more in its data centers based on power consumption, right? So yeah, those are all great things to do.
But I will say for a lot of the academic community where they've been conditioned to view that high-performance computing cycles are free, that this is part of a broader sort of cultural change. So because certainly at scale, you're on a large job. You are consuming real dollars, right? Or yen or euros, depending on your flavor.
Can I add one more thing?
Please.
I would also say a lot of our, at least from federal government and our executive order, a lot of our big users are excluded facilities when we report energy intensity from a sustainability side. And I think that's something that we should really push to change, because if it's excluded, it's kind of like, oh, well, whatever. I don't care how much energy I use or water I use because it's an excluded facility. So I think that's something else. If we get researchers and people and users to really care about that, and it becomes not excluded anymore, I think that's another big incentive and kind of cultural, political change.
So what's interesting, Dan mentioned we give them reporting on the dollars used or maybe on the energy used. Think about, and I know we're not there yet today, but think about in the future our resource allocation committees, right, where you actually give allocation to all of your users. We've done them by CPU hours, we've done them by GPU hours. In some cases, we've done them by dollars, and then they can consume. Some of them have done it by energy. Maybe we could do it by carbon footprint. And then we'd basically tell the users, you have so much budget in carbon emissions that you can run for your allocation period, and then they actually get to make the smart choices and go compute and try to optimize.
Carbon emissions is great if it brings in the dynamicity of the grid. Energy cost, more than total energy, I think is important. If you don't, otherwise you won't bring in the dynamicity.
We all know metrics reward and punish, and people will optimize to the metrics to which they're exposed. Yes.
Hi, Alan Cantle, OCP HPC subproject technical lead. I would like to touch back on to the rip and replace view. And what we're trying to do in the OCP high performance compute subproject is redefine computing architecture from the ground up with energy efficiency and sustainability in mind from the ground up. But the sad news is that needs a complete redesign. And we are all driven by making commercial returns in two to 3 years from our innovations. Is there any way around that so we can actually start to build data centers so we can do incremental updates and they're much more efficient in their architectural design from the sustainability perspective?
This is a great question. I think this is actually kind of a holy grail we need to try to achieve as a community. There are ways to do it. And I think we've been guilty of, for instance, trying to achieve maximum absolute density, right? On systems like exascale systems where you're going with PCB boards that are like 25 some or more layers because it's so dense. And then what's driving all of that density is that you're trying to cram so much chips per area. And so there are things, for instance, like if we were to embrace faster like deployment of optics, then you have like midboard optics or passive optics connectors, then that actually allows you to not be so coupled to density and not have to drive so exotic designs from a hardware perspective. And maybe that's a way to actually go and enable easy, more reusable standards going down the road. But this is, maybe we can chat offline. This is a very long, complicated question.
It's the commercial dynamics. We used to have research and development years ago, but now it's all development for the next 2 or 3 years. And I think that's the problem. We can only evolve. It's an evolution. We can't do a revolution. We need a revolution.
Amen to that. So
I agree.
We're almost out of time, and you two have been waiting patiently, so here's what I'm going to suggest. That each of you step up, ask your question, and then we'll combine that with offering the two panelists a chance to offer any final comments. So please both ask your questions.
Sure. Michael Ott with the Leibniz Supercomputing Center. So I would like to come back to the whole heat reuse topic. So I really have a hard time thinking about our industry ever becoming sustainable by rejecting megawatts of heat into ambient air. And I mean, we have the technology now, right? We have direct liquid cooling, we can run high temperatures. So the same technology that allowed us to get away from chillers and use free cooling year round, maybe you should pronounce a bit more that the same technology can be used for heat reuse. And maybe we just need to stop building the data centers in the places we are building them, where we can actually make use of the heat. And Nick, I'm not sure whether we should grow tomatoes in a place where we need heating like 2/3 of the year, but I guess it's a step in the right direction. And also then if we reuse the heat, then also the whole topic of water usage disappears because we don't need any dry coolers or evaporative coolers anymore.
Okay.
Thanks.
Hi, I'm Todd Rosedal. I used to work at IBM and I work for JBL now. I've been involved in this community. So I'd like to comment on something Alan was bringing up. So having this revolution of a brand new way to build this compute efficiently is great. But even right now in OCP, there is this MHS initiative. I don't know, Nick, if you know about that, but it's this modular hardware server where all the pieces inside the server are being defined mechanically and electrically. And so you can just pull out this HBM board, which is the processor module, and everything else can remain. You don't have to do the rip and replace. But I understand your density thing, but I just want to point that out. You might want to look at that or join that OCP working group and maybe help steer it.
Okay, 2 comments, questions? Panelists, final thoughts.
Final thought, I'll just kind of actually talk about the heat reuse, just that was one of the last topics, is it's so promising. Just the problem right now is the co-location of the need for heat in the data center. It's just such a huge problem. You can't do energy reuse in every single data center. So I think people are going to be smarter as the planning goes on in the years ahead. The other thing I'm hoping, I'm wishful for, as we talk about the higher temperatures and liquid cooling, is HPC and AI push the, let's say, the commoditization of liquid cooling. And then if you're able to do that for any kind of compute, and then it all becomes more efficient and more stuff to heat reuse. But in any event, you got to measure it.
Yeah, I think that we should be a little bit more innovative what comes to the heat reuse. So we should think about the new systems and new ways to reuse the waste heat from the system. It's not only the district heating, but like a fish farms in Norway, and they are heating the swimming pools and other things from the waste heat of the data center. So we should think more in the community how we can utilize the waste heat from the data centers.
Yeah, I agree with that. It's really hard to retrofit a facility that doesn't have a waste heat situation already kind of set up. It's really expensive, and like we said, really depends on co-locating and your weather and climate and all of that. I would say just final thoughts is I think there's a lot of different solutions. I think we've talked a lot about location is a really big issue in terms of energy and water and kind of what method you choose to go to for your particular data center. And then I think in the future, building a facility that makes sense, that has all these features already in it, depending where you put it, if it's a brownfield, are all like really important things. So I think there's a lot of stuff that we can do in the future for when we build these new facilities of like what makes sense and where to put them, and really be thoughtful about that.
So let's see. Having been pushing this notion that computing needs to think about its environmental sustainability for a number of years now, I couldn't be more encouraged at the number of people in this room and the interest and the engagement and the action by industry and so on. So that's super positive. I'm still a little worried that the framing that most technologists think about and most industry folks think about is a little bit too narrow. If you look at the progress of Moore's Law over the last 50 or 60 years, the increases in energy efficiency are astronomical. You know, many orders of magnitude, I don't know, 10, 12, 15. So any amount of efficiency increase could still lead to massive growth in consumption and massive growth in environmental damage. So I think that we have to face the reality that society is likely at some point to start pressing on us to say, it's not good enough that you're a little bit more sustainable, you're a little bit more sustainable. You have to find a way to contain the overall environmental impact of all of the activity of all of computing. And HPC is a piece of that, cloud is a piece of that, mobile devices are a piece of that. And that constraint becomes much more severe. So I think the bar is very high for what we, as a community, need to achieve over the next 5 to 10 years.
And for my closing comments, I'll kind of add a little bit to what Andrew was saying. I think it's really important the community starts procuring in a more open the box, if you will, blend the OpEx and CapEx together, include the water consumption, include really the carbon emissions and everything like that. And the industry, right, the vendors, the system integrators, push us, right? Push us, drive it, through your RFPs, through your engagement with the vendors. And we have the tech, it's out there, but we have to move away from the walled garden of between OpEx and CapEx and pure procurements that are based on flops per dollars. We have to elevate and procure a lot more holistically. So that would be my big takeaway for you guys.
And I guess I'd just offer the following. We all know whatever part of the world you're in, the boom around AI has caused governments to think deeply about what policies are appropriate for our society. It's a symptom of what I would say is a larger issue. Many of us who are older grew up in a world where computing was kind of an oddball curiosity. It's now a critical global infrastructure that consumes a statistically significant fraction of our global energy. And in the face of that, plus climate change, there really are social imperatives to think about this. And so unlike other infrastructure that's thought about these issues for a long time, we're playing catch up, but we have to do more. And with that, thank you all for being here. I know the panelists will be happy to chat some more, but I'll echo what Andrew said. The fact that you're here says there's hope. So let's keep working on the problem. Thank you.